Taking a look in this video at graphical analysis, specifically how we put together all the pieces we've learned about position and velocity graphs, and talking a little bit about acceleration. We're going to start with a little recap on signs of acceleration. So I would say take a moment and see if you can pick which sections of graphs and which direction, which sign the acceleration will have. For speeding up in the positive, slowing down in the positive, speeding up in the negative, and slowing down in the negative directions. Pause the video if you need to before we go on. So when we think about speeding up, we are talking about a velocity that becomes larger or a greater magnitude. Slowing down is heading towards zero. And the positive direction means positive velocity, and the negative direction means negative velocity. And so with that in mind, if we start with A is clearly showing a positive velocity to start that goes to zero. So we get negative acceleration for segment A. B is showing starting at zero and going to a negative, which would also be a negative acceleration, but that's showing heading in the negative direction. V versus T graph here, we look at C, where we start with a negative velocity and we go positive. That is a positive change or a positive acceleration, slowing down in the negative direction. And finally, for D, the only missing piece, we start at zero velocity and we go to a positive velocity. So that's going to be positive acceleration. I'm going to give you two other questions that I want you to write down the answer to, and we'll revisit them at the end of the video. Given this displacement profile, right, we have a curve. Is the acceleration always negative? Is it positive at first, then negative? Negative at first, then positive? Or negative, then zero, then positive? So I'll give you a moment on that. Remember, we're talking about acceleration, and this is a displacement profile. Pause the video if you need to think about it and write down your answer. It may help to think about a velocity time graph that comes from this and then think about acceleration. The other scenario I wanted to look at is the cart rolls beyond the point shown. So it already came down the hill, and now it is going to be sliding on the last lower piece. As that happens, no friction, just free to slide, are the acceleration and the speed, or speed and acceleration, are they both going to decrease, both going to increase, or will speed increase but acceleration decrease, or the opposite, speed decreases and acceleration increases? So again, write those down. All right, so our goal today, calculate the area under the curve for acceleration time and velocity time graphs. And we'll know we understand this if given any one of those, the three graphs we have, position time, velocity time, or acceleration time, we can create the other two. So far, we've learned that you can take the slope of position time to get velocity, velocity time to get acceleration. And our goal today is to look at how we go from velocity to position and acceleration to velocity, those two graphs as well. So another way of thinking about this is thinking about where we need more information. So if you look at these velocity time graphs, all three of them actually have the same exact slope, right? And so any one of them would have the same acceleration graph, a horizontal line with a positive acceleration. So there's something we're missing here. If I want to go from the acceleration time graph and pick which one of those is specific to my motion, I need an extra piece of information, an initial condition, or sometimes we call it a side condition, to pick which one is correct. And the easiest thing to know would be what was our initial velocity? If I tell you we had a positive initial velocity, that top line has to be correct. And so we can eliminate the rest of them. This comes from doing the area under the curve or integration, which we'll get to eventually. The constant of integration is really the piece we're dealing with here, that initial condition. So when we talk about area under the curve, we're saying that given any velocity time graph and one extra condition, we can find the graph of position. Same thing with acceleration. Given that graph and one extra condition, we can find the velocity time graph. We're finding the area under the curve, we call it, but it's really the area between the line of the graph and the horizontal or time axis. For example, if we have a case here where we have some velocities given, right? A positive velocity, then a segment of zero velocity, then a segment of negative velocity. We can find how much displacement or distance traveled in a particular direction for each of those three intervals, and we can kind of put that together to figure this out. Notice we have our initial condition, x naught equals 10 meters in the positive direction. So we can start out by thinking of the definition of average velocity, delta x over delta t, which means our delta x is the amount of average velocity, or in this case, constant velocity, multiplied by time. So for the first segment, we start with our initial condition, positive 10 meters. Then from 0 to 5 seconds, we have this area here, which has an area of positive 20 meters, 4 meters per second times 5 seconds. The new data point then should be 20 meters further along in the positive direction from where we started. So that means 30 meters. We can say during this segment, we're going to just connect the dots because it's a constant velocity, so it should have a constant slope. The next segment from 5 to 10 seconds, our velocity is 0. So that means we're going to cover 0 additional distance during that time. And so over those 5 seconds, we still have the same position. And again, constant velocity, so that's a straight line. Then from 10 to 25 seconds, we have a negative velocity, which means we're going to be heading in the opposite direction. And that area under the curve, you might say, oh, it doesn't really seem like it's under the curve. But remember, this is between the curve and the line. This is in the negative part of the graph. And so if we think of this mathematically, it has a height of negative 2 meters per second and a width of 15 seconds for negative 30 meters of displacement, which means if we started at 30, right, we now head back toward the origin, and the new data point at 25 seconds is actually at the origin, right? Negative 30 meters from where we were before. We can connect that line, again, a constant velocity with a slope of negative 2 meters per second, or meters per second. And so that's how we do that. We can do some more. Move myself out of the way, right? If we have a velocity graph, we can actually start with that and go to acceleration by figuring out what the acceleration graph looks like simply by taking the slope, right? From 0 to 10 seconds, slope gives us 0.4 meters per second. From 10 to 15 seconds, the slope is 0. And from 15 to 20 seconds, the slope is negative. So we have a negative segment. We have these vertical lines there that are not really, all these kind of sharp corners don't really work for physical motion, but everything is piecewise continuous. So once we've done that, I'm going to cover up the acceleration graph while we talk about how we get the position time graph. Now here we no longer have constant velocity segments. So if we look at our first segment, well, first our initial condition of 0 meters, then we start thinking about the area of this segment. It's a triangle, so we have to use 1/2 base times height. Or in other words, you're sort of thinking of the average velocity, which is half of that 4 meters per second, multiplied by the time over which that occurs for positive 20 meters displacement. The new data point is at 20 meters from the origin at 10 seconds. The dots are going to be connected, but they're no longer going to be a straight line. They're going to be a curve because you start out slow, 0 velocity, so a flat or shallow line, and you get steeper and steeper because you're getting faster and faster. And so that gives us our curve on the position time graph. And the positive acceleration is going to be curving up in this case, right? Getting steeper. 10 to 15 seconds, we have 0 change in velocity, so 0 acceleration, but we have a constant velocity of 5 meters per second, giving us positive 20 meters of displacement. The new data point will be 20 meters further on, so at 40 meters. And because this is a constant velocity, this gets a straight line saying. From 15 to 20, we have another segment. We are slowing down, but we're still heading in the positive direction. So the area under the curve could be found by finding the area of a trapezoid, if you know that formula. I never remember, so I always just do the triangle and the rectangle. But whatever it is, positive 15 meters works just fine. Or the triangle and the square method and rectangle method also work. But basically what you get is another graph up there, but this time it's curving to flatten because we are talking about slowing down. We start out with the high velocity, steep slope, and the low one. So what do we have? We have the idea that if we want to go from a position graph to a velocity graph, we can take the slope. A velocity graph to an acceleration graph, take the slope. We want to go the other way. We use the area under the curve, but we need an additional piece of information. So we can always read information directly from these graphs, find the slope, or find the area. So revisiting that first question we had, if we look at this graph, it shows that we have a positive velocity at first, going to zero velocity and then heading to a negative velocity. And if you look at the velocity graph, that has a negative slope, so that's always a negative acceleration. Similarly, on this one, what happens on the frictionless ramp? Well, as it flattens out, you're not going to be accelerating as fast, so your acceleration actually decreases until you're on a flat surface where there's no acceleration, but you're still going to be speeding up as you slide down that ramp. All right, if you want to try more of these, in the Unit 1 packet, pages 19 through 23, there's a bunch of practice with position and velocity graphs and acceleration graphs. Think carefully about the shape when you are connecting the dots. Think about the acceleration for which way it curves.